Deep beneath the lavender fields of southern France, inside a concrete cavern larger than 3 football fields, French engineers are about to activate a facility that will change global nuclear politics forever. The building they're standing in shouldn't exist. According to American intelligence, what France is attempting is technically impossible without U.S. help. But in the coming months, this underground factory will begin producing weapons-grade uranium completely independently, using a technology so advanced that even the Americans don't have it at this scale. The facility they've built is called Pierrelatte. It contains over 1,400 stages of uranium enrichment, consumes enough electricity to power a major city, and required solving engineering problems that had never been encountered before. According to declassified CIA documents, American intelligence estimated this plant would start production in late 1966 or early 1967. They were watching closely because if France succeeded, it would break America's monopoly on large-scale uranium enrichment technology. This is the story of Pierrelatte, the most ambitious nuclear engineering project you've never heard of, and the underground factory that proved a medium-sized nation could achieve technological independence against all odds.
To understand why France built this secret uranium factory, we need to go back to November 1956, the Suez Crisis. France and Britain had just launched a military operation to retake the Suez Canal from Egypt. They expected American support. Instead, President Eisenhower threatened economic sanctions and refused to provide emergency oil supplies unless they withdrew immediately. But here's what terrified French military planners. During the crisis, Soviet Premier Nikita Khrushchev sent threatening messages to both Britain and France. According to declassified U.S. intelligence documents, Soviet notes constituted strong threats of military action and even suggested the Soviets might use rocket weapons against the Anglo-French forces. The Soviet Union possessed hydrogen bombs and the missiles to deliver them. France had neither. General Charles de Gaulle, who would become president in 1958, drew a stark conclusion from Suez. France's security could not depend on American nuclear protection. The United States had just proven it would abandon its allies when its own interests diverged. France needed its own nuclear deterrent, what would become known as the force de frappe, or force de dissuasion. But there was a massive technical problem standing in the way. Building nuclear weapons requires enriched uranium or plutonium. France had successfully built plutonium production reactors. The G1, G2, and G3 reactors at Marcoule were already operating. These could produce enough plutonium for basic atomic bombs, and France successfully tested its first plutonium device, Gerboise Bleu, on February 13, 1960, in the Algerian Sahara. The device had an explosive yield of approximately 70 kilotons. But plutonium weapons had limitations. They were bulky, required complex triggering mechanisms, and weren't ideal for France's ultimate goal: compact thermonuclear warheads that could fit on ballistic missiles. For that, France needed highly enriched uranium, and that meant mastering uranium enrichment, one of the most difficult industrial processes ever attempted. Here's why enrichment is so challenging. Natural uranium contains only 0.7% of the isotope U-235, which is what actually undergoes fission in nuclear weapons and reactors. The other 99.3% is U-238, which is useless for weapons. To make a bomb, you need to increase that U-235 concentration to over 90%, weapons-grade material. The problem? U-235 and U-238 are chemically identical. They have the same number of protons and electrons. The only difference is 3 neutrons, making U-238 just 1.3% heavier.
Separating them is like trying to sort identical twins by weighing them. Three enrichment technologies existed in the early 1960s: electromagnetic separation, which had been used in the Manhattan Project's calutrons but was inefficient; gaseous centrifuges, which were promising but still experimental; and gaseous diffusion. Gaseous diffusion was the only proven industrial-scale method. The Americans had built massive plants at Oak Ridge, Tennessee, and Paducah, Kentucky. The Soviets had their own facilities at Novourovsk and Siversk. But here's what terrified French military planners. The Americans had spent over $2 billion, equivalent to over $20 billion in today's money, developing gaseous diffusion technology during the Manhattan Project. The K-25 plant at Oak Ridge was the largest building in the world when completed, covering 44 acres under one roof. And the Americans weren't sharing. The Atomic Energy Act of 1946, also called the McMahon Act, made it illegal for the U.S. to share nuclear weapons technology with any nation, even Britain, their closest ally and partner in the Manhattan Project. The law imposed fines up to $100,000 and imprisonment for up to 5 years for anyone who disclosed restricted nuclear information. France faced a dilemma: build your own gaseous diffusion plant from scratch with no blueprints, or remain dependent on American nuclear protection forever. De Gaulle's decision was immediate and absolute. France would build its own uranium enrichment. On June 17, 1958, de Gaulle formally decided to build a uranium enrichment plant at Pierrelatte in the Drôme region of southeastern France. Construction began in 1960 in a remote area about 30 kilometers from the famous wine region of Châteauneuf-du-Pape. What the Americans didn't know was that French engineers were about to solve problems that would make their facility comparable in some ways to anything the United States had built. But the biggest challenge was still ahead.
Before we can appreciate the engineering achievement of Pierrelatte, you need to understand exactly how gaseous diffusion works and why it's one of the most demanding industrial processes ever attempted. First, uranium metal must be converted into uranium hexafluoride gas, called hex by engineers. This is the only uranium compound that's gaseous at reasonable temperatures. The hex is then pumped through thousands of stages arranged in a cascade. Each stage contains a barrier, a thin membrane with billions of microscopic pores. When hex gas is pushed against this barrier under pressure, the slightly lighter U-235 molecules pass through fractionally faster than the heavier U-238 molecules. Here's the brutal reality. Each stage increases the U-235 concentration by only about 1.3%. According to U.S. Nuclear Regulatory Commission documents, to go from natural uranium at 0.7% U-235 to weapons-grade uranium at 90% plus U-235 requires approximately 1,400 stages. Imagine 1,400 separate units, each containing compressors, heat exchangers, and barriers, all connected by thousands of kilometers of piping, operating continuously for months without any contamination or breakdown. Now here's where the engineering becomes almost impossibly difficult. Challenge 1: the barrier material. The barrier membrane is the heart of the entire process. It must have billions of pores, each approximately 10 to 25 nanometers in diameter, about 1/10,000th the width of a human hair. Make the pores too large and there's no separation, too small and the gas can't pass through efficiently. The barrier must also resist corrosion from uranium hexafluoride, which is one of the most corrosive substances known. It attacks metals, plastics, and most materials on contact. The barrier must remain stable at high temperatures while maintaining perfect pore structure. The Americans had developed barriers using complex proprietary processes, but the exact manufacturing methods were the most closely guarded secrets of the nuclear age. Security around barrier production was even tighter than for bomb designs themselves. France had to independently develop its own barrier technology. According to declassified National Security Archive documents, French researchers developed 3 types of barriers: alumina-based, nickel-based, and Teflon-based designs. A special facility for uranium processing was established at Le Bouchet, near Paris, which had been France's first uranium facility, starting in 1946. The barrier production occurred under extreme security. Workers couldn't know what they were making. Each person performed one step of a multi-stage process without understanding the final product. Challenge 2. The compressor problem. Every stage requires a compressor to push gas through the barrier. With 1,400 stages, that means 1,400 compressors running 24 hours a day, 7 days a week, for years without failure. These aren't ordinary compressors. They must handle highly corrosive uranium hexafluoride gas without any leaks. A leak doesn't just waste expensive uranium. When hex contacts moisture in air, it produces hydrofluoric acid, one of the most dangerous substances known. The compressors must also operate in a precisely controlled environment. If any stage overheats or cools unexpectedly, the hex can solidify, blocking pipes and destroying equipment. French engineers had to develop completely new compressor designs. The reliability requirement was staggering. With 1,400 compressors, if each had a 99% reliability rate, you'd still expect 14 failures at any given time. That's unacceptable when the entire cascade must operate as one integrated system. The solution was redundancy and preventive maintenance on a scale never attempted before. Backup compressors were installed at critical stages, and specialized maintenance teams were trained to service the equipment using procedures that took years to develop.
Challenge 3. The power consumption crisis. Here's a problem that almost killed the project before construction even began. A gaseous diffusion plant of the size France needed would consume enormous amounts of electricity, enough to power a major city. Where would this electricity come from? France's electrical grid in 1960 couldn't supply that much power to a remote location in the Drôme region. Building conventional power plants would take too long and cost too much. The solution was audacious. France would build dedicated nuclear power reactors to provide electricity for the enrichment plant. The reactors would be built at Marcoule and later at the nearby Tricastan site, which eventually housed 4 large pressurized water reactors. There's a beautiful irony here. These power reactors would produce plutonium as a byproduct, which could be extracted for additional nuclear weapons. The enrichment plant, designed to produce uranium weapons material, would be powered by reactors producing plutonium. France was building an integrated nuclear weapons complex that made efficient use of every component. Challenge 4. The cooling system. Compressing gas generates enormous heat. With 1,400 compressor stages running simultaneously, Pierrelatte would generate as much waste heat as a large city. All this heat had to be removed continuously, or the equipment would fail. The solution required building one of the largest industrial cooling systems in Europe. Water would be drawn from the Rhône River through a specially constructed system. The cooling water infrastructure required its own pumping stations, heat exchangers, and treatment facilities. Challenge 5. The cascade configuration problem. The cascade must be carefully configured so that uranium flows from stage to stage with optimal efficiency. Too much flow in one direction and you waste energy. Too little and the process is inefficiently slow. American plants used cascade configurations based on their Manhattan Project experience. French engineers, working independently and needing maximum efficiency with limited resources, had to develop their own cascade designs with sophisticated flow optimization. This required solving computational problems that pushed the limits of 1960s computer technology. The calculations were performed using early French computers at research centers, with some assistance from the growing aerospace industry's computing resources.
But what they didn't know was that construction would bring unexpected challenges that would test every assumption.
In 1960, construction began at Pierrelatte, and immediately nothing went according to plan. The site chosen was not ideal from an engineering perspective. The terrain was difficult, a mix of limestone and clay that complicated foundation work. But the location offered something more important: isolation for security, proximity to the Rhone River for cooling water, and access to the electrical grid that would be expanded with dedicated nuclear reactors. The project initially operated under various cover designations to obscure its true purpose: weapons-grade uranium production. This was classified at the highest levels of French government. The construction site itself was enormous. The main gaseous diffusion complex would eventually cover approximately 50 hectares, about 120 acres. Unlike the American plants built as single massive structures, the French design used multiple interconnected buildings, each housing sections of the cascade. This modular approach was born from necessity. France couldn't afford or build the massive single-building approach, but it offered an unexpected advantage. Sections could be started up and tested independently before the entire plant was operational. Security during construction was extraordinary. Workers were divided into teams that worked on isolated sections without knowing what adjacent teams were building. The barrier manufacturing process was so secret that components were built in different facilities and only assembled at Pierrelatte. A dedicated security force was established. The entire facility was surrounded by multiple fences, guard towers, and state-of-the-art intrusion detection systems for the 1960s. Aerial photography of the site was prohibited by French military order. But here's what made construction especially difficult. They were building a facility for a technology they hadn't fully proven yet. Normally, you develop a technology in a laboratory, test it at pilot scale, then build a full production facility. France was trying to do all three simultaneously. Research on barrier materials continued even as the Pierrelatte buildings were rising from the ground. According to historical records, the first low-enriched uranium was produced at Pierrelatte in January 1964, proof that the basic technology worked. But this was still far from weapons-grade material, which would require the full cascade operating at high efficiency. Construction challenges were constant. One unexpected problem was vibration. With 1,400 compressors running simultaneously, the building complex would vibrate at specific frequencies. Engineers discovered that at certain operating conditions, these vibrations would resonate with building structures, potentially causing equipment damage. Solutions required installing thousands of vibration dampening systems and redesigning some building foundations. Acoustical engineers were brought in to analyze vibration patterns and develop solutions, expertise borrowed from the aerospace industry. Another problem was contamination control. Even microscopic particles entering the cascade could block barrier pores or damage compressors. The entire facility had to operate with clean room levels of air quality, extremely difficult for an industrial-scale chemical process. French engineers developed sophisticated air filtration and pressure control systems. The buildings were maintained at carefully controlled pressures with air handling systems that consumed enormous amounts of energy, but were essential for safety and equipment protection. Cost overruns were significant, though exact figures are difficult to verify from public sources. What is clear from historical records is that the project faced substantial budget pressures and timeline delays, yet de Gaulle's government remained committed to completion. By the mid-1960s, major construction was complete. The buildings were finished, thousands of kilometers of piping were installed, compressors were in place, and electrical systems were energized. Now came the moment of truth, starting up the most complex industrial facility France had ever built. But the real breakthrough came when they finally brought the system online.
The startup of a gaseous diffusion plant is not like flipping a light switch. The process takes months and must be done with extreme care. First, every section of the cascade must be evacuated to remove all air and moisture. Even tiny amounts of contamination can ruin barriers or cause catastrophic chemical reactions with the hex gas. Then, inert gases are flowed through the system to test for leaks. With thousands of joints, valves, and connections, finding and fixing leaks is a massive undertaking requiring teams of technicians working continuously for months. According to a declassified CIA intelligence report from the mid-1960s, the Pierrelatte gaseous diffusion plant was scheduled to start production in late 1966 or early 1967. Historical records confirmed that the facility did indeed become operational during this timeframe. The startup process was methodical and careful. Each stage would be tested individually before being integrated into the cascade. Each compressor would be run for extended periods under monitoring before uranium hexafluoride gas was introduced. The startup team consisted of approximately 150 engineers and technicians, many of whom had been training for this moment for years. They worked in shifts to maintain 24-hour coverage. Every parameter, pressure, temperature, flow rate, vibration, was monitored and recorded. When uranium hexafluoride was first introduced into the cascade, this was the moment of greatest risk. If the hex reacted violently with any contamination or moisture, it could cause a chain reaction of failures through multiple stages. The flow rate started at a small fraction of design capacity. Engineers watched gauges intently. Every hour that passed without failure was a victory. Gradually, over weeks and months, the flow rate was increased. More stages were brought online. The lower sections of the cascade were activated first, producing slightly enriched uranium. Then middle sections came online, and finally the upper stages that would produce weapons-grade material. By 1967, according to Princeton University research on military fissile material production, Pierrelatte was producing highly enriched uranium for weapons and naval fuel at this facility. France had successfully built and operated one of the most complex industrial facilities in the world, completely independently, in approximately 7 years from project initiation to weapons-grade production. Within months of full operation, France had enough enriched uranium for uranium-based thermonuclear weapons. By the late 1960s, France possessed a complete nuclear deterrent with both plutonium and uranium-based weapons, deliverable by aircraft and eventually by submarine-launched ballistic missiles. The technical achievement was extraordinary, but maintaining operations would prove to be an ongoing challenge.
Running Pierrelatte continuously proved almost as difficult as building it. The facility operated nearly continuously year-round, shutting down only for brief maintenance periods. The workforce grew to over 2,000 people, including engineers, technicians, security personnel, and support staff. Operational challenges were constant. Barrier failures occurred regularly, not at catastrophic rates, but frequently enough that barrier replacement became a continuous activity. Specialized teams worked to remove and replace failed barriers while the rest of the plant continued operating. Compressor maintenance was performed on strict schedules. With 1,400 compressors, maintenance became a perpetual activity, with teams constantly inspecting, servicing, and replacing components. The environmental impact was significant. The facility consumed enormous amounts of electricity and water. Waste heat discharged into the Rhone River raised water temperatures measurably for kilometers downstream. Depleted uranium, the U-238 waste product from enrichment, accumulated at enormous rates. This material, still mildly radioactive, had to be stored in specially designed facilities. By the time operations ended, France had accumulated vast quantities of depleted uranium requiring long-term storage. But from a strategic perspective, Pierrelatte achieved exactly what de Gaulle intended. By 1968, France possessed an independent nuclear deterrent capability. The country was no longer dependent on American protection or permission. When France withdrew from NATO's Integrated Military Command in 1966, it could do so knowing its security rested on its own nuclear forces. The technical knowledge gained at Pierrelatte had broader applications. French engineers became world experts in gaseous diffusion technology. In 1973, the Eurodiff consortium was established as a multinational uranium enrichment organization, with France as the leading partner, based largely on expertise from Pierrelatte. Georges Besse, one of the key engineers involved in the Pierrelatte project, went on to become CEO of Eurodiff in 1978, demonstrating how personnel from the military program transitioned to civilian applications. He later became CEO of Renault in 1985, where he led a successful turnaround of the company. Tragically, he was assassinated on November 17, 1986, outside his Paris home by the French terrorist group Action Directe. He was shot multiple times and died almost immediately. The facility operated successfully for 45 years. However, gaseous diffusion technology is extremely energy-intensive. As more efficient gas centrifuge enrichment technology matured in the 1980s and 1990s, Pierrelatte became economically obsolete. A new facility, Georges Besse II, using modern centrifuge technology, was built at the Tristan site starting in the 2000s. It began operations in 2009 and uses approximately 50 times less electricity to produce the same amount of enriched uranium as the gaseous diffusion plant. The original Pierrelatte gaseous diffusion plant shut down on June 7, 2012, after 45 years of operation. According to the plant operator, it had seen uninterrupted operation since the late 1960s and had met the enrichment needs of around 100 power reactors in France and around the world. The facility is now being decommissioned, a process that began officially in 2020 and is expected to take until 2040 or beyond. In 2025, demolition work began on the two massive cooling towers, each 123 meters high, which had become iconic landmarks of the site. But here's what makes Pierrelatte truly remarkable from an engineering perspective. France accomplished in 7 years, with limited resources and no external assistance, what the United States had taken over a decade and massive investment during World War II and the early Cold War. French engineers independently developed barrier materials, compressor designs, cascade configurations, and operational procedures that matched American capabilities. They did this while under intense time pressure, with limited computing resources and without the benefit of espionage or technology sharing that accelerated some other nations' nuclear development. Pierrelatte represents one of the great engineering achievements of the 20th century, not because it was the most technically advanced facility, but because it was built completely independently against enormous odds. The project demonstrated that determined engineers, given clear objectives and sufficient resources, can solve problems that experts claim are impossible. And that lesson extends far beyond nuclear technology.
The story of Pierrelatte resonates today for reasons beyond nuclear history. In our current era, nations and companies face similar challenges. How to achieve technological independence when critical technologies are controlled by others. Think about modern semiconductor manufacturing. Companies like ASML in the Netherlands hold near monopolies on extreme ultraviolet lithography machines, essential for advanced computer chip production. Several nations are currently trying to develop indigenous semiconductor technology to escape dependence on specific suppliers,
facing challenges eerily similar to what France confronted with nuclear enrichment in 1960. Or consider space launch capabilities. For decades, only a handful of nations could independently launch satellites. Now, new companies and nations have developed independent capabilities through determined engineering and innovation. The Pierrelatte model: identify the critical technology, commit resources, accept that it will be harder and more expensive than planned, solve problems systematically as they arise, is being repeated across industries and nations today. From an engineering perspective, Pierrelatte also demonstrates the value of different approaches to the same problem. French cascade designs and operational methods differed from American approaches in specific ways, sometimes offering advantages born from different constraints and requirements. There's rarely one correct solution to complex engineering challenges. Constraints that seem like disadvantages, France's limited computing power, smaller budget, lack of existing blueprints, can force innovative thinking. The environmental legacy is more complicated. Depleted uranium storage, radioactive contamination from decades of operations, and the energy consumed all represent real costs. Modern enrichment, using centrifuges, is far more sustainable, which is why gaseous diffusion has been abandoned worldwide. But we must judge Pierrelatte in its historical context, a time when environmental concerns were secondary to strategic imperatives. When nuclear energy seemed like the unlimited power source of the future, and when the memory of World War II made national security the paramount concern. The people who built and operated Pierrelatte were not reckless. They were engineers solving unprecedented problems with the knowledge and tools available in the 1960s. Today, the original Pierrelatte facility is being carefully dismantled. The massive buildings that once consumed as much power as a large city are being decontaminated and demolished. In another 20 years, little physical evidence will remain of the underground uranium factory that broke America's nuclear monopoly. But the engineering lessons endure, that complex problems can be solved through systematic approaches and determination, that technological independence is achievable even for medium-sized nations, and that sometimes the most important innovations come from being forced to find your own solution rather than copying someone else's. That spirit, the refusal to accept technological dependence, the determination to solve problems regardless of difficulty, is why Pierrelatte succeeded. And it's a spirit that's needed just as much today.
If this story of underground uranium factories, innovative French engineering, and the cascade technology that changed nuclear history fascinated you, you'll want to subscribe to this channel because we specialize in the technical problems and engineering solutions that shaped military history in ways you've never heard before. Coming up next, we're diving into how Soviet engineers built entire secret cities like Arzamas-16, erased them from all maps, and somehow convinced tens of thousands of people to live and work there, designing nuclear weapons, while the rest of the world had no idea they existed. You'll discover how they solved the infrastructure problems in cities that weren't supposed to exist, how they transported nuclear materials through the Soviet rail system without revealing what they were carrying, and how Soviet designers conducted calculations with the computing tools available in the 1950s that today would require supercomputers. Hit that subscribe button and make sure notifications are turned on, because these are the stories of how impossible engineering problems were solved under extreme pressure. Stories that reveal the hidden technical history of the nuclear age.
And if you want to dive deeper into French nuclear history, check out our video on the Mururoa Atoll testing site, where French engineers had to build an entire nuclear testing facility on a coral atoll in the middle of the Pacific Ocean, one of the most remote and challenging construction projects on Earth. The engineering brilliance behind military history isn't just about weapons. It's about human ingenuity solving problems that have never been solved before. And those stories are worth remembering.